You told me recording in progress and that this webinar is being recorded. Hopefully you got a similar message so you know that that's happening. Remember that you can use the chat, you can use the Q&A. I'm going to bring it up so I can see the Q&A. Here we go. And that way you can participate without having a recording. Thank you so much for joining us as we begin another year of online Superstellar Fridays. I'm going to be honest, I kept waiting last year for that moment when I could say, okay, we're going to see each other. This is going to be fantastic. And we're just going to wait a bit longer, obviously. So I really appreciate that you're here to start a new year of this with us. And what we're going to look at tonight is something that came out of a conversation I was having with an educator at the Mount Washington Observatory. And we were talking about space science, ways to understand space in different places in space. And their comment to me was, well, you know, there's weather. We could talk about space weather. And I thought, well, yeah, you can talk about space weather, but it's one thing to say, this is the coldest place, or this is the place that has the strongest winds, or, you know, that we've ever recorded. But that doesn't necessarily tell you what it's really like on a day to day or year to year. You know, that tells us about like specific moments in time. But if we're talking actually about going someplace and staying there, that's an entirely different way of looking at it. That's climate instead of weather. And so that was kind of the seed for this idea of looking at what the climate was like. And I realized as I was doing research into this, that first of all, I didn't know very much. I mean, I knew about some things, but I really didn't understand some of the dynamics of the moon and Mars. But the other thing that was really interesting was there was so much information on Mars. It was so easy to find. And the moon was much more challenging. And which surprised me in some ways, because I thought, well, we've actually been to the moon. I feel like that should be, it's closer. We've studied it so much. That should be the part that's easy. And then I have to really push for the Mars information. And it was the opposite. And I don't know why that is. I don't know if that's because we've been to the moon. So, you know, we're moving on already. Or if it's just that in terms of what's going on in the moon or on the moon, as you'll find out, maybe it doesn't lend itself as much to talking about versus Mars. So it was kind of interesting in terms of what I found as I was doing this. But I found some amazing graphics. I'm really excited to share them. People have worked really hard to help us understand what it's like in these places. And so I'm hoping you'll kind of get a sense of that too, and also get a sense of what's in store for the astronauts who are going to be making those journeys and spending that time in those places. So I am going to get us started with sharing my screen. Here we go. Okay. So hopefully you can all see that, and I'm going to put my chat over here so I can kind of see it. So if I look really distracted, it's because I'm looking in different directions at once. But hopefully what you can see right now is a picture of Mars right there. And I called it extra Earth climates just because I really wanted to get into more of the long-term trends and the overall picture of these places. And I focused on the moon and Mars because those are definitely next steps for NASA and for other groups as well. I mean, I know we talk about journeying farther. We talk about wanting to understand as much as possible. And when we talk about interests that we have in places like Europa, because maybe there's some liquid water and other things hanging out under the icy crust there, or we talk about, you know, visiting Venus because it is so close or something like that. But really the moon and Mars are kind of where it's at. And part of that is proximity, obviously. It's still 3 days to get to the moon. So when we talk about a journey, when we talk about doing something, going to a place and being a presence there, it's still difficult to get to the moon, let alone Mars. Remember that Mars is moving around the sun, as we're moving around the sun. So there's all sorts of calculations that happen. And typically when it works out well, we're talking about a 9-month journey. So it's still difficult to get to these places, let alone going even farther. So I thought, let's concentrate on what we know are the next steps that NASA is planning for here. So that's what we're going to look at it. And you'll see that, you know, in some ways they're places that are very familiar to us, but I definitely learned a lot as well while I was doing this. And I wanted to start off with, with some images that we might have of what it means to live in an age when we're going between planets or going to the moon and back again and staying in these places and everything. And so one of these images actually is from NASA. It was drawn by one of their artists to help us kind of visualize a base, an extra Earth base. The other one actually comes from the Jetsons because I felt like it kind of encapsulated some of the ideas that we have about futuristic scenery in terms of these flying machines to get from place to place and you know, these encapsulated areas that we'd be living in that are, you know, kind of protecting us from whatever environment is around us. And so that's kind of where I'm starting with, because I felt like these would be familiar, but also interesting to refer back to a little while later. And certainly many people have imagined what it means to live on the moon, on Mars, or in other locations in space. And I think as I kind of go through some of what would be in store for them, we'll recognize that some of these designs, I mean, they work, but they're probably not the best in the long term. So let's see what I can do. There we go. So starting off with the moon. And the moon is, right, is our familiar space. We're so used to seeing it all the time. But I don't know how much we actually think about what it's like there or what the dynamics are. So just to help us imagine this space, think about the moon's cycle, right? We're always seeing the same side of the moon just because of how it's turning as it's going around us. We always see that same side. And that side takes 27 days, a little more than 27 days, to go through its full cycle, right? Of starting with a new moon that you can hardly see. It grows through the first quarter to a full moon. It starts to decrease through the third quarter back to the new moon. That's the 27 days cycle. That also happens to be one lunar day. Because if we think about it, what we're seeing during that 27-day cycle, we are seeing essentially the sunlight make its way across that side of the moon one time. So one lunar day is 27 Earth days. That means that the moon gets 324 hours of sunshine, followed by 324 hours of darkness. It's a really long day. That's a really long night, just in and of itself. But then we need to think about kind of the lighting and heating dynamics of that. So 27 days to go through heating up and then cooling down again. 324 hours of constant sunshine. And remember, I mean, there are a number of factors going on here in terms of temperature and all of those things. But remember, we're not talking about any clouds. There are no rainy days, anything like that. It is constant sunshine for 324 hours on any one spot. And then it's constant darkness for 324 hours. So you're getting that buildup of solar energy and then a long-term loss. So you see some really big swings in temperature as a result of this. I mean, think about what happens for us on a hot day. And then just imagine if our day kept going and going and going. Another thing that's really interesting about the moon, at least in terms of comparing it to the Earth, is it has a tilt, but it's a tiny, tiny little tilt. It's about 1.5 degrees. That will be important later on, as you'll see. But what it means effectively is there are no seasons on the moon. We think about Earth's seasons. That's coming from our tilt, right? That for part of the year, you know, the southern hemisphere is closer to the sun. For part of the year, the northern hemisphere is closer to the sun. And so we're getting that switch of more solar energy, less solar energy as you go throughout the year. So you get seasons, but that doesn't happen on the moon because the tilt just isn't enough. It's pretty much year round the same all of the time. So that would be, I'm not saying that would be a problem for us, but it would definitely be some sort of adjustment in our heads, in our minds about what a year meant. Because if we're used to a yearly cycle of this change, and instead it's a year of exactly the same all the time, that requires a bit of a rethink about what it means to experience a year. just to give you a sense of how much those temperatures can be high or low. This information is coming from what's known as the Diviner Lunar Radiometer, which is one of the pieces of equipment on the Lunar Reconnaissance Orbiter that's constantly going around the moon and scanning for all sorts of important information. But this one specifically is the temperature, just to kind of help us understand. And as you might expect, red is hotter, bluer is colder. I do want to point out that when we're looking at this scale right here, okay, we are talking about kelvins, at least in the picture. So when you're kind of looking at those numbers, just remember that like 0 Kelvin, which we're not seeing here, just to point out, but 0 Kelvin is like complete zero, absolute zero, essentially, of matter. So just kind of adjust yourself a little bit that way, but still, it's a huge swing. So if we were to translate it into Fahrenheit, highs of 260 degrees Fahrenheit, lows of negative 280 degrees Fahrenheit. So that's a huge swing, right? That's more than 500 degrees between highest and lowest. And that's going to be essentially your daytime swing. And granted, your day is 27 Earth days, but still, like, that's your daytime swing. And if you notice this center line down the moon there, this kind of transitional part of the orange ready, that's really small in comparison to the really warm and the really cool. So you're really hot and there's a quick transition where you cool down and now you're really cold. And then there'll be a quick transition and you heat up and now you're really hot again. And this absolutely has already caused challenges for the astronauts who went to the moon because they had to be prepared. I mean, space itself can be very, very cold. So you had to be dealing with how do we stay warm? But at the same time, there is the possibility of really high temperatures on the moon. So now you've also got to be able to deal with those high temperatures and cool yourself down. So those swings can be a huge problem depending on how you're trying to deal with them. But I wanted to point out that there actually are places that never get warm. So both of these images are, once again, the Diviner Lunar Radiometer. And they're showing, once again, heat. Red is hot, blue is cold. If you notice, daytime and nighttime temperatures at the very bottom here at the poles, we've got blues and purples all the time. And the reason that we have that is that tiny tilt. That 1.5 degrees is just enough so that there are certain craters, there are certain areas and craters that are always in shadow. And we think, not positive, but we think that these craters, especially in the South Pole, could contain water ice that remained from one time when there was more water on the moon. So you've got these really high temperatures, these really low temperatures, but then you've got a couple of areas that always have low temperatures. And so we've measured almost negative 400 degrees Fahrenheit in the southern pole areas in some of those craters, and that's weird, I can't say that, below 400, negative 400 degrees Fahrenheit in the northern part. So like negative 413 Fahrenheit is the coldest we've measured in the northern pole. And negative 396 degrees Fahrenheit is the coldest we've measured at the southern pole. So you've got these areas that just never get warm. Part of the reason that they never get warm is that there's just a very thin atmosphere. I mean, people talk about it as no atmosphere. That's not entirely true, but it's just so thin, it's not really doing anything. There are molecules there of gas in the atmosphere. It's just that they're so few and far between that they're not really doing much. And that means that they're not able to hold on to the heat and they're not able to buffer either. So we've got this massive warm up, this massive cool down, and it happens quickly because it just can't hold on to the heat. There are also a constant stream of impacts, right? We've seen lots of craters on the moon. There are always new craters on the moon. There have been periods in the past where many more things were hitting the moon, but I mean, it's still a regular occurrence. So we're talking about a place where you don't have an atmosphere that can burn up small objects coming toward you. You're going to have an impact instead. So you've got to be ready. Whatever kind of base you're building needs to be ready for a regular rain, essentially, of rocks coming down. Another really big issue when we talk about living on the moon is the magnetosphere, or magnetic field, or lack thereof. So based on some information, some research that's been done and data that have been collected, we believe there was a stronger magnetic field in the past. We believe that it used to have the Earth's magnetic field is partially generated by the fact that you've got the liquid in the core, but then also solid. And so the movement of the solid in that liquid and that constant turning is an internal dynamo. And that constant turning is what gives us a really strong magnetic field, which is quite helpful to us. It protects us, it helps us find north, all sorts of things. We think that the moon had that at some point, but it was definitely in the past. We're thinking there might have been this internal dynamo, but the magnetic field that exists today seems to be on the surface. It seems to be mostly kind of in the crust. So it's probably coming from the materials in the crust, like iron and things like that, rather than this internal source. And what that means is that the moon is definitely at risk. So the picture here that I'm showing you, and we're gonna look at a couple of different versions of this because I found some cool stuff. The picture here is kind of showing you the Earth, and this clear space trailing out behind the Earth is essentially the magnetic field. And you'll notice that it's kind of trailing out behind, and that's because of the solar wind. The solar particles coming from the Earth, from the sun, they're moving at 280 meters per second. So they are this wind, and it comes and it hits the Earth's magnetic field. It kind of squishes it on the side closest to the sun and then pulls it out, elongates it back behind there. But if you notice, these are all the solar particles right here, all of these things, they're all being rooted around, or most of them are being rooted around the Earth. And so our magnetic field is protecting us from solar radiation, solar particles. There's also cosmic background radiation, all sorts of things. But when they interact with our magnetosphere, they're kind of channeled, and that protects us. The moon doesn't have that. And the moon doesn't have that for a couple of reasons. First of all, it doesn't have a strong enough magnetic field. As you can see in this picture, the moon is just kind of there in those particles. It's casting a shadow, so clearly it's grabbing some particles, but it doesn't have this buffer out in front of it, okay? But there are a couple of other things that are happening too. So this is an animation that I found that gives you a good idea of the fact that sometimes the moon is protected actually by the Earth's magnetic field. There it goes. It's in the magnetic field. We're safe. It's a buffer. But because of how it rotates, right? Sometimes the moon is closer to the sun than we are. Sometimes it's further away. There are periods where the moon is completely exposed to the solar wind and all of that radiation. And it doesn't have the atmosphere and it doesn't have the magnetosphere. And then it kind of dips back behind, which we thought meant that there were periods of the moon being protected and periods of the moon not being protected. We thought that there was kind of like this going back and forth again. And then we learned that every now and then a pretty massive solar pulse would change this. And I'm going to give you a better visual for this one, which is once again really cool. This is a solar pulse, a huge pulse of solar particles coming toward the Earth. You can't really see the Earth, but you can see that green space that is within the magnetic field. And then the black circle on the left, that's the moon, okay? Now watch, as the solar pulse comes, it narrows. It's enough force that it narrows the magnetic field of the Earth so much that the moon is now outside of that protected zone. So even though the moon's behind us, because there was this solar pulse coming through, now the moon is exposed again. And we didn't realize how often that happened. We thought that was maybe every now and then kind of thing when you had a special solar pulse. And then we found out more recently that even if the solar winds are coming at a funny angle, the same thing can happen. So the moon is actually more exposed to radiation than we had originally thought, and it's pretty exposed to radiation. And so that's a concern. And so the fact that there's, really nothing to halt or redirect solar and cosmic radiation is a real concern on the moon. And so that's one of the reasons that I grabbed this picture from NASA, because it looks very nice. It's a moon base, they're exploring, they're doing all sorts of different things. But I thought, like, they're totally exposed. They're on the surface. So unless you're using a huge amount of lead, You can use water, but water is also incredibly heavy transport. Unless you're doing those things, probably people are only on the surface for short periods of time when it's safe. And then, you know, when needed, they're actually spending a lot of their time below ground. Okay, so it looks to me like Jessica raised their hand. So if you would like to talk, I have unmuted you.
Go ahead.
What? Why does the solar system shrink when the red hits the green?
Okay, so here's what I want you to think about. Have you ever seen a fan that is turning? You know, it's like on a stand and it's kind of like turning back and forth to fan a big area.
Yep.
And then if you're standing in a spot, right, you might, maybe while the fan is pointed in a different direction, there, you know, maybe you're feeling a little bit of wind, but not too much. But then as it turns toward you, suddenly you're feeling all of that pushing on you, that air pushing on you. It's the same kind of idea. So there are always tiny little solar particles coming off of the sun. It's happening all the time. But every now and then there'll be like an eruption on the sun's surface. We call it a coronal mass ejection. And it's just a whole bunch of material and energy that erupts out of the surface. And a lot of it falls back down onto the sun because the sun has a lot of gravity, but there's still lots of little particles that now just get shot off into space. And they're kind of like the wind from the fan. As they're going through space, they have so much energy that they're pushing against things. And what's happening in this picture is not so much that the solar system is getting smaller or anything like that, but kind of the area around the Earth that's where all of these solar particles are being pushed by our magnetic field, that area is getting smushed, essentially, because there's just so much pressure coming from the sun with that big pulse. Does that make sense?
Yep.
Cool. Okay, I'm gonna, if a moon base was created from modules like the ISS, would these be safe to live in? That's a yes or no. That's a yes and no question. There is no question at all that astronauts who are on the ISS are exposed to greater levels of radiation than here on Earth. There's no question about that. However, because of how they're doing things to protect, yes, it is certainly less. You could do that. The problem is that the ISS is lower down in our atmosphere. I mean, we think of it as space, but to be perfectly honest, the ISSs are still within our atmosphere. So it still has a certain amount of buffering, and it has the ability to change things in its position and its orientation a bit. And you wouldn't necessarily have that on the moon. So one of the suggestions has been, if you want to do something on the surface on the moon, do it in a crater. Do it in a crater that has at least one section that's almost always in shadow. Of course, that means it's really cold. But, you know, that was one suggestion. Another suggestion was simply to dig down. There are definitely lava tubes and things like that under the surface of the moon. So another suggestion had been, why don't we put the base where people are spending most of their time under the surface so that they've got more protection, and then they're coming up onto the surface to do the work, that kind of thing. But it would limit, they'd have a much safer place to withdraw to if there was a real problem, and it would limit their day-to-day exposure. I'm gonna show you, I couldn't find a map of radiation for the moon. I was kind of frustrated, but I found one later on for Mars. And Mars' atmosphere is actually a little bit thicker than the moon. So it'll give you an idea of what we're talking about in terms of radiation exposure. And it is definitely much higher than what we see on Earth and even on the ISS. Okay, so let me keep going. So anyway, returning to our moon base here, like I brought it back just to be like, yeah, I mean, it's good, but I don't think it's really where they're going to be spending most of their time. I think probably something else, just because we know that the solar radiation is a problem, so why not address it rather than say, well, it's just there. Okay, Mars. And as I said, I found so much more on Mars. Like I really did. So Mars in some ways is really similar to us. Days are roughly the same, slightly longer, right? 24.6 hours. The year is twice as long, essentially, because it's got to go further around the sun. But it's, so if you think about it as like winter would be twice as long, summer would be twice as long, that kind of a thing, because the tilt itself is pretty similar to ours. So when we're talking about seasons, Mars definitely has seasons. And, 25 degrees is not that far from ours. So it would be a very similar experience that way. But Mars didn't always have this tilt, which I think is fascinating because I didn't know this at all. And it's changed quite a bit. So just to give you an idea of how much the tilt has changed over time. So we believe it may have been as little as 0 degrees, so straight up and down, and as much as 60 degrees. There are some conflicting, I've seen 15 to 35, that kind of a thing, but certainly much less of a tilt and much more of a tilt than we see right now. And this was a very, very long-term process. I do want to say that, but we think that the reason we don't wobble, the Earth actually does have a little tiny bit of a wobble, but it's not nearly the wobble that we see with Mars. But we think the reason that we don't have this same wobble is because we have our moon. So for those of you who are not familiar with Mars, has 2 moons, Phobos and Deimos. They are quite small. They're definitely not round. They're essentially asteroids that were captured by Mars gravity. And so when you're talking about something that, for example, is only like 2 miles wide, it is a tiny bit of rock going around a planet. And so it really doesn't have a huge amount of gravity to exert over Mars, whereas our moon is pretty good size. I mean, it's obviously not as big as the Earth, but when we talk about kind of mass-wise and width-wise and things like that, it's about a 5th, 6th. So it's got much more gravity, and it seems to have stabilized us by having it pulling on us consistently. It seems to have stabilized us. Well, Mars doesn't have that. And so the wobble that Mars has over the long term is really interesting. If you look over here on the left, this is showing you like that change in its tilt up and down over time as it continues around, like versus ours. It's a huge change. And when it's changing, when that tilt is changing, it's absolutely changing what it's like on the planet. When it's up and down, you're not having seasons, first of all. When there's no tilt, you don't have seasons, but also you're going to be seeing that you've got some, generally colder, and you've got ice caps, at least for Mars, near the poles. However, when the tilt starts to get more and more and more pronounced, what you're doing is you're taking those poles and now you're tilting them toward the sun, right, or away, so that now you're getting kind of more variation on the poles, and you have melting. And in the area that would be the equator, and this is what's being shown on the right-hand side, the area that would be the equator is now actually developing ice caps. And so what we saw, at least over the long term, and I mean tens of millions of years, is this redistribution of ice, so that the ice would start at the poles, and then over time you'd have melting at the poles and ice forming at, more around the midsection, the equator, as that tilt gets really extreme, and then the tilt goes back, and so the ice melts at the equator and ends up back at the poles again. So that's a huge change. And I mean, it's over millions of years, so it's not like we would necessarily experience that, but it's part of why the Martian landscape is the way that it is, because you have these big redistributions on a regular basis of where the ice is. So that's one part of the tilt, but it turns out that Mars also has a tiny little wobble too that's happening. So it's got a lot going on. And so let me get to our next. This picture is a cross section of the ice caps specifically of the northern polar ice cap. And I want to point out that there's water here, there's water, ice here, but a lot of the ice that we find on Mars is actually carbon dioxide. So just to point that out, we're talking about, it's water ice, but it's other ice too, just in terms of our experience. And if you notice, you can see that there are layers here. And those layers are kind of alternating bands of ice being put down and then some dust, and then ice being put down, and then there's some melting and dust, and so on. And what we're seeing there is about 104 to 107 year cycles of some ice put down, and then there's some melting, and then some ice put down, and then some melting, and that kind of thing. So there's this larger wobble, and then there's the smaller little tiny wobble too. So there's a bunch of stuff happening on Mars, which, over the long term we need to think about, but certainly for our experience, the tilt is very similar. The seasons that we would see would be pretty much the same. The one difference, or I guess the one accentuated difference that we would see in terms of these seasons. So Mars is going around the sun in the same way that the Earth is going around the sun. And if you think about the Earth's orbit, it's not a perfect oval, right? It's not perfectly centered. We've got this more kind of elliptical orbit so that when we're having summer in the Northern Hemisphere, we're actually a bit further away from the sun than when the Southern Hemisphere is having summer. So that's part of the reason that we get warmer summers in the Southern Hemisphere and cooler summers in the Northern Hemisphere, is because of just how we're a bit further away when it's our turn to have summer. And it's the same thing for Mars, but accentuated considerably more, so that it's even further away for northern winters than it is for southern winters. And I'm going to show you a graphic of what that looks like. So, they've kind of accentuated that, but otherwise it's going through the same kind of processes that we would see. It's a normal year, just taking twice as long for it to go around the sun. And so we have these, versus the moon, where everything's just kind of all the same on one side or the other. We actually have zones, areas that are warmer, areas that are colder. And this is relative. So I'm going to show you some temperatures. So this is relative, but basically, if we're looking at the equator, it's definitely warmer in those areas. When you're getting up towards the poles, it's definitely cooler. And so remember that you've also got all sorts of valleys, you've got craters, you've got mountains, all sorts of different formations that are going to impact things on a local scale too. But this is, basically how we would see it, which is very similar if we think about our own world, our own Earth. We think about that we've got our tropical rainforest kind of spanning the equator, and then you've got still hot but drier kind of above and below that, and then you start to get into our temperate zone and eventually work your way toward the poles. So it's a similar thing. But to give you a sense of how equator on Mars is a different experience than equator for us. So Curiosity is the rover that is currently active in Gale Crater. And it turns out that Curiosity loves to provide weather reports. So you can get all sorts of information. And so this is Gale Crater, where Curiosity is recording weather. And someone at NASA has taken the time, which I love, to compare it to Los Angeles. So we're looking at actually 2 years here, right? Because in Mars, we're dealing with a different scale, right? It takes 2 years for them to go around and everything. But just to give you a sense of what we're talking about, if you notice, Los Angeles is at the top of this graph right here. So you can kind of see how the temperatures are going up and down depending on if it's summer or winter. Gale Crater is at the bottom because it is much colder in Gale Crater. And I'll show you exactly where this is in a moment, but just remember that, we're not talking about the polar regions of Mars, but it's still much, much, much colder. And then notice that the temperatures in Los Angeles, they're ranging, maybe 20, 30 temperature, degrees in a day between high and low. But Gale Crater is going through, I'm looking maybe 100 degrees difference in the course of a day. Okay, so we have much bigger differences between high and low temperature on Mars. And here's where we also see that the longer winters and shorter summers for Gale Crater, because of where it is, it's a bit farther away when it's got its summertime temperatures and things like that. And so I actually, if you want to know, Curiosity will tell you exactly what the weather was recently. So this is the most recent report as of this morning that I could find from NASA. So it's, mid-December, but still. Here we go. So our maximum temperatures, we hit a high of 23, which is kind of similar to us. If we think about our high temperatures in the winter, sometimes 23 isn't unreasonable. But our low temperature of negative 105 is pretty extreme. And if you notice the sunrise and sunset information, what we're seeing is this is fall right now, actually. The days are getting shorter. If you look at this, I think I did that right. So we've got like some changes there. We've also got some changes in the temperature, and it's a huge swing. And that's one of the big concerns, at least, about Mars is once again these huge swings, but generally cold. And this right here is Gale Crater, just so that you know, like I didn't choose someplace in a polar region. This is pretty well near the equator. It's just that because of some things to do with the atmosphere, which I'll talk about, and features and things like that, it's not getting particularly hot there. It's warm for Mars. Average temperature on Mars is negative 80. So it's warm for Mars, but it's not particularly warm there. Now, Curiosity is not the only robot that's sending us information on weather. So I also found from InSight. Unfortunately, InSight started having trouble transmitting the information starting at the beginning of 2021. So you can see that some of this stuff gets cut off there. But here's what I want you to notice. So InSight's in a different location, and I'll show you where in a moment. But I just want you to notice the temperature InSight is dealing with is pretty much the same all the time. There is not a huge amount of variation where it is. It is simply cold all the time. That's just what it's dealing with. But if you look, the air pressure is changing regularly. We've got these huge swings in air pressure, which are connected to seasonal changes. And the very bottom row is actually saying opacity or opacity. What we're talking about is like dust in the air, that kind of thing. And we'll talk about the dust storms in a moment. So you can see other factors are changing, but that temperature is just cold all the time. And this is Elysium right here. This is where InSight is. So a bit further north, still really not in a polar region, but it's just cold all the time right there. And so if we're looking at kind of average temperatures that our astronauts would be dealing with, it can get as hot as 95 degrees Fahrenheit. We've definitely recorded that. But typically on the equator, you're going to be talking about hot is 70. And when you're talking cold is negative 225, that kind of thing. So Mars has these temperature swings and it has these seasons, but from our perspective, it's pretty much cold. It's always colder than what we're used to right here. The other thing that happens with the temperature has to do with the atmosphere. So I want to get us to this point. Okay, so high temperatures, yeah, here's that information. And we've got that elliptical orbit. So I found this really neat animation that actually takes you through 2 years of daytime temperatures right here. And it does a great job. And there we go. It does a great job of illustrating how you see summertime in the south. Now summer is moving north as we're changing. So you see that seasonal variation right there, but you also see how it gets much warmer in the south than it does in the north. Those high temperatures in the north cannot compete. So it is that warmer summer in the south. The other thing I want you to notice as you watch it and you kind of look through it, there is a moment, I'm going to play it again. There's a moment where it's really warm and then suddenly something changes. And so we'll kind of go through it. There we go. We're heading back toward it's warm, it's warm, it's warm. And suddenly there's like a blip right there. Okay. And we're going to talk about that blip because something changed. There was an event at that point that caused that blip. Normally you wouldn't have such a rapid transition in Mars. Oops, sorry, there we go. And that has to do in part with the weather in the atmosphere. So the atmosphere is there, but it's really thin. It's 100 times thinner than Earth's, which means that once again, we're heating up, we're cooling down pretty quickly. We're not able to hold on to heat as well. We think that probably Mars had a thicker atmosphere in the past, but it was stripped away by solar winds. And Mars also doesn't have that magnetic field, that magnetosphere to really protect and hold on to its atmosphere. So there are challenges there as well. Most of Mars' atmosphere is carbon dioxide. And when I say most, I mean 95% of Mars' atmosphere is carbon dioxide. In comparison, carbon dioxide makes up 0.038% of Earth's atmosphere. So it's a much smaller percentage. And even when we talk about, nitrogen, which is the largest component of our atmosphere here on Earth, it's not even close to 95%. So Mars has a huge amount of carbon dioxide. And that's why when I talked about the ice, it wasn't just water ice, it's carbon dioxide ice. And it's more of a carbon dioxide cycle that we see in terms of thawing in the summer, freezing in the winter. And so in many cases, the water ice at the poles is actually covered by carbon dioxide ice that's been deposited afterward. And this thin atmosphere does have some interesting weather patterns. There are these dust devils, essentially, that get started on a regular basis. And sometimes the dust storms can become so big that they actually engulf the entire planet. And so when we saw that blip of a sudden cool down, that sudden cool down was because now all of a sudden we have a planet-wide dust storm. We notice that the dust storms are more common in spring and summer, and we think it's because they're basically keeping themselves going. So a little bit of dust starts moving, it gets kicked up, and now it's higher above the ground. So it's getting that solar radiation first, warming up even more. And so it keeps moving and keeps moving. And now it develops into this dust devil or tornado. Although to be perfectly honest, they're still not incredibly strong compared to the tornadoes we deal with. Maximum winds tend to get around 60 miles per hour, which is still strong, but it's not on the level that we deal with here on Earth. We also believe that the dust devils are more common, the dust storms are more common when the tilt gets stronger, so that we wouldn't see when that tilt is at zero. It's not, the axis isn't leaning. We don't think there are nearly as many storms as when you've got that strong tilt right there. So we've got this kind of thin atmosphere, and the thin atmosphere, in addition to not being able to hold on to heat over the long term, it would actually make you feel it on a regular basis. Like it basically, if you were standing on Mars, there would be about a 15 to 20 degree difference in temperature between what your head was feeling and what your feet were feeling, which to me, I have trouble understanding that, but that's how thin the atmosphere is in terms of distributing the sun's heat, so that you would actually notice that as a person, I mean, I'm not very tall, but as a person who's definitely not with their head on the ground, I would feel like my head was much colder than my feet, actually. And then the radiation bit, and this was the map that I mentioned before. So the map is showing cosmic radiation values on Mars. I think we could probably use it to think about the moon as well. I couldn't find one like this for the moon. But if you look at this, so blue areas get less exposure to radiation, red areas get more exposure, and there are even a couple that are kind of light, which are big. The couple of things that I want to point out about this, if you look at the scale at the top here of cosmic rays, so the doses are like 10 to 20 rems or rads per year, just to give you a sense of what Earth exposure is like. The average person on Earth is exposed to 0.6 rads per year. So Mars scale is already more than 10 times this. So there's that issue right there. And I did try to find out what kind of was considered safe for an astronaut, because I was wondering, at what point does NASA say this doesn't work very well? And I couldn't it was in a huge technical document. I did do my best, but I couldn't piece out where the astronaut information was. But I did find out that NASA would consider someone who's working on Earth, but dealing with radiation exposure because of whatever their job was. So maybe they're working near a nuclear facility or something like that, that for one of their workers on Earth, 5 rads or REMs per year would be considered the maximum dose you'd want to go for. So once again, Mars is double or more that. So radiation on Mars really is, once again, a big concern, just like on the moon. So, you know, we have to think about, it's not just, can you handle the temperatures? It's not just, can you handle the weather? What is it like for seasons? All of those things. It's also, you're very exposed because of these thin atmospheres, because of the lack of magnetosphere. And so how do you deal with that as well? Okay, a couple more things that I just wanted to point out, because when I found out about them, I thought they were amazing. So I mentioned that Mars doesn't have a magnetosphere, doesn't have a magnetic field, but it turns out that it borrows one every now and then, which is really fascinating. And this, I don't know that this would necessarily influence what it's like on a day-to-day basis living there, but it definitely changes our understanding of the environment and the atmosphere there. So what can happen is that as the solar wind is actually coming towards Mars and it starts to kind of be wrapped around the planet, there is a magnetic field traveling within the solar wind, and that gets wrapped around the planet as well. And it basically kind of excites electrons within the atmosphere to move up and down. So that you get the development of electric currents in the atmosphere, moving up and down. And so when you look at this, the yellow arrow is showing the direction of the solar wind. These kind of blue-green strands, that's showing us the magnetic field kind of wrapping around the planet. And then the red arrows and the blue arrows are showing the movement of current up and down. And I found that absolutely fascinating, that within the atmosphere, there are simply electric currents moving because of how the solar wind is interacting with the planet. But obviously, if you were in a place that had electric currents, you would need to be thinking about, what does that mean for being up off the surface of the ground? Is it possible for those currents to really intensify, kind of things like that? So you'd have to be thinking about that weather as you're doing it. I just thought that was amazing, personally. And then I wanted to mention the other thing that make one of many things that can make being on Mars really extreme is it does have some huge geological features. For example, the biggest mountain in the solar system, which is Olympus Mons. And so if you remember back to that picture of cosmic radiation, there were a couple of spots that were white. Those are those big mountains that are just poking up even more through that very thin atmosphere. So the exposure is even greater at the top of those mountains. And so kind of thinking about how to work in places where the geography is going to, and the geology are going to help you, as opposed to put you at greater risk, is just another concern. So that is my presentation on the climate of Mars and the moon. I hope that I wanted to find out, like, are there any places that would be similar? Because how do you understand? How do you conceptualize and figure out what this really means? So here's what I came up with. Not really. There really aren't places that are like it, but there are places that help us understand. So here are 3 places that NASA regularly uses for training, and not just for astronauts, but also equipment, like figuring out what's really going on. Can they handle this stuff? So the one on the left, that's Death Valley. Death Valley is used on a regular basis because it is so dry, because it has those extreme swings of getting really hot, really cold. This is one place where astronauts are sent to work. It also, because it's quite barren and everything, it looks the part as well. So that's one place that people use. The middle picture is Iceland. It's actually the interior of Iceland. So if you're on the outside, the outer edge, the coastal area of Iceland, you see a lot of green. But once you get into the interior, because there are so many volcanic eruptions, and maybe you heard about the recent one that was happening outside of Reykjavik, there are so many volcanic eruptions, and there are so many regular lava flows happening there that it's created something of a moonscape or Marsscape, because it really is just lots of loose, pieces of volcanic rock with these flows over them. And so in terms of understanding the terrain, Iceland is a good opportunity for that, just to kind of better understand what it's like to move in the space. And then the picture on the right is the Atacama Desert in Chile, which is the driest desert in the world. And it is a place where you have, once again, extreme temperatures in terms of very low temperatures, but you also have this sublimation, this freezing and then thawing into gas process happening on a regular basis. And that's what this is showing you. These are ice, sculptures essentially, where ice, the moisture has condensed and frozen from gas. And then it will be moved by the wind and then go back into gas, so that you've got these kind of different dynamics. It's not the same that we would see in terms of rain and stuff like that. So once again, to help astronauts understand what it is like up there, that's kind of what we're talking about. So if you guys have any questions, I will do my best. You pretty much got all of my information right there, but I'm happy to do what I can to answer or find answers if I do not know them. So if anybody has anything, please add it to the chat or the Q&A. Hopefully you found this just as interesting as I did. I have to say, Mars blew me away. The electric currents, like I had no idea. And that was just a lucky thing, because I was just trying to find, like, okay, is there a magnetic field? Can I find out more about the history of that? And suddenly this popped up. And do those currents ever mess with curiosity? Right, that was my question, right? Because you would think, and then I was thinking about Ingenuity, right? The helicopter. And so maybe I'm thinking that these currents must be high enough off the ground. And I don't think that Ingenuity made it more than 50 meters up. So I think that probably when you're right by the surface, it's not such an issue. But I would think that entering the atmosphere might be a concern. Like, you might need to be aware of that, especially if you're not a probe that's kind of like all nicely encapsulated or something like that. I would think that would be a concern. Yeah, if we were to live on Mars for 1 year, the radiation is scary. It is amazing, right? I mean, that is, and it's not something that we always talk about. One of the real challenges is that the things that we know that work well for radiation, like lead, like water, stuff like that, are so heavy. So bringing them with us is so difficult. That's why it's not that we don't know how to deal with them. It's that how do we make it work in a space environment is the much bigger challenge, I think. Does the solar wind reach out as far as Neptune and Pluto? In fact, much, much further. So the solar wind, if you look at it, obviously it kind of gets less and less as it gets further out. But if you were to think about, our solar system is big. I want to stress that it's huge. If you've ever seen kind of like a visualization of the Oort cloud, which we kind of think of as like the outer remnants of our solar system, where we are is just so small in it. The solar wind goes out far enough that it's all of the planets, it's quite a few of the dwarf planets, it's quite a few of the comets as well, and things like that. Now, some comets are actually coming from outside of the solar wind, but if we look at it this way, so Voyager 1 and Voyager 2 were launched at the end of, well, mid to end of 1977, which means that they have been traveling for, well, about 44 and a half years. And 2 years ago, they made it to the edge of the solar wind. So they had been traveling for more than 40 years to get to the edge of the solar wind. That's how far out. And so what happens when you get to the edge of the solar wind is you're still in the solar system, but now those objects like comets and other things that we're not entirely sure of that are out there, those other objects are still gravitationally held in. They're still bound to the sun because of the gravity issue, but they're not dealing with the solar wind at that point. given the radiation levels, is it realistic in humans? I would think so. I mean, but I think it's a matter of figuring out how to minimize the risk. I mean, one of the things that we had talked about at the Discovery Center when we were kind of imagining what it was like to live on the moon was that we figured we probably wouldn't spend a huge amount of time on the surface. We would have robots that we sent up to deal with stuff, and we would go up when needed, but we would be able to try to minimize risk that way. And my guess is that it would be the same thing on Mars. I think probably the bigger challenge is the getting there, the exposure during getting there, because once you're there, you know, if you could get underground, then now you've got better protection. So I think it's more the travel is the bigger concern, since we know about the radiation. Would it be safer radiation-wise to live on Pluto instead of Mars? Well, Pluto, oh wow, that's a really good question. Pluto has more of an atmosphere. So right there, you've got a bit of better protection, and it is further away. One of the challenges, just to point out, there's radiation and then there's other radiation. So there's like solar radiation and cosmic background radiation and all sorts of radiation. So you might kind of be swapping some, because you're farther away from the sun, less, the solar wind isn't as strong right there. You might be swapping that for other stuff. But because Pluto does have a bit more, it's still a weird atmosphere. It freezes at night and it thaws during the day. So it's still a really weird atmosphere. I don't know if you'd be able to dig down as well, though. I don't know if you'd be this protected digging down, just because there's a lot of ice there, as opposed, it might be harder to create something stable. I'd probably go for Mars, but I could be totally wrong about that one. Okay. Crust of the moon versus Mars for digging to create habitat. I mean, Mars, so when we look at the moon, what we're really seeing is basalt. It's a lot of volcanic rock. And so there was a number of volcanic eruptions during the kind of creation of the moon's surface, and then the cooling, and then it's been covered up by all of these rocks, dust because stuff has hit the moon, those kinds of things. So we know that there are lava tubes under there. We know that just kind of based on how magma is moving under surfaces and things like that, there are probably places that if we knew where to go, we could find areas already hollowed out for us. And it is basalt and other volcanic rock. Mars soil seems to be more of a, I don't want to call it a sandstone thing, because that suggests that it's like on Earth, and I don't think it's entirely like that, but we know that it's able to be worn away by water. We know, because we can see the riverbeds and lake beds and things like that, the deltas that are left over. So we know that that's possible. And from what I understand, InSight is digging down into the ground, and they were having a huge problem because as it was digging, they were having trouble getting enough traction for it to continue pushing down, which suggests to me that the rock there might be easier to dig into, but I don't know how crumbly it would be in comparison. So I don't know if that answered your question, because I don't know that I could compare them, but I know that they're different. Okay, are there any other questions? I'll give people another moment just in case they're still thinking of something. I do want to encourage you to check out NASA's sites and images and video for both the moon and Mars. The LRO, the Lunar Reconnaissance Orbiter, which I mentioned earlier, is a satellite around the moon. There are researchers at UNH, Andrew Jordan is one of them, who work with that. They're specifically interested in radiation levels, so that's what their aspect of it is. But it tracks a whole number of things. And then some brilliant people at NASA have really worked hard to help you visualize what it means. So I really encourage you to check it out, because it was just amazing. I mean, I was blown away. So I hope that you enjoyed it as well. And thanks for joining me tonight. So we're going to keep doing this as a virtual experience for as long as it makes sense, safety wise, but I'm really looking forward to seeing you all again at some point. And I'll be sending out information about February. So if everything works out, I'm excited about this. We've got a group of students from UNH. We're going to talk about their work. And they're much more aware of the outer space environment than I am. So I'm sure they will understand much of this a lot more than I did. But I'll send out that information. Everyone will know. And I hope you guys have a wonderful evening, a wonderful weekend. Enjoy it. And I hope that you're having a great start to what I'm really hoping will be an improving year. So good night, everyone.